We're going to start on a new chapter today on acids and bases. A lot of the different substances that we interact with every day are actually either an acid or a base. So we see that both in biology, where DNA is deoxyribonucleic acid, and medicines and drugs that we take are also basic in nature. So we're going to talk a little bit about just the general characteristics, which are things that you can observe about acids and bases. One is just that acids tend to have a sour or tart taste to it. So you tend to find acids a lot in citrus fruits. So if you eat these type of fruits like oranges or grapefruits, they tend to be quite sour or tart. And that's a sign that they have a number of different acidic components in them. Bases, on the other hand, tend to be bitter and have a slippery feel to them. So things that contain bases, for example, are cleaning solutions, detergents, soaps, etc. You take some medicines that contain bases, you'll notice that they have really bitter taste to them. Now, one of the most common ways we test for acids and bases is we use these compounds that are called indicators. And basically, they are substances that will turn one color if they're exposed to acids, and they'll turn a different color if they're exposed to bases. The most well-known of these indicators is probably litmus. And so litmus will turn red if it's exposed to an acid, and it will turn blue if it's reacted with a base. Now, acids and bases are chemical opposites of each other. So if we put the two of them together, they react in what we call a neutralization reaction, converts both of them to a neutral species. And the neutral species that's created is water. The reaction is often called the neutralization reaction. Now, as you'll see in a second, one way we recognize acids is by looking for hydrogen in its formula. An acid's formula starts with an H, and typically we're talking about aqueous acids. So that means that these are hydrogen-containing compounds that are dissolved in water. So you also see AQ following the formula that the acid is written in. Bases tends to contain hydroxide or OH groups. And so if you see anything with an OH, it's likely that they're going to have basic characteristics. There is a base that I want you to know that doesn't have any OH, and that's ammonia or NH3. So once we know the observable behavior of acids and bases, we need to think a little bit about how we define acids and bases molecularly. So the first person to have a definition of an acid and base is Arrhenius, and how he defined it is an acid is something that will produce H plus ions when it's dissolved in water. H plus ions is what we call a proton, because if you think about hydrogen in the periodic table, it contains one proton and one electron. When you write it as H plus, that means that electron has disappeared, so the only thing that's left is proton. So we often call the H plus ion, the hydrogen ion, also proton. So an acid is basically a compound that would, when dissolved in water, produce a proton. A base, on the other hand, according to Arrhenius, is something that will produce the hydroxide ion when we dissolve them in water. The presence of water here is critical, because without water, these compounds would not be acids or bases. So they do need water in order for them to release those ions. So for example, an acid would be HCl aqueous. So that aqueous is critical to include. And when we put these in water, these compounds break apart or dissociate into the separate ions, in this case H plus ion and chloride ion. Now it turns out that H plus actually doesn't really exist, because it's such a highly charged ion and it's small that it will want to neutralize itself. So things in our universe are not stable when they are highly charged, and the H plus, as it's floating around, is looking for negative charges. There is a lot of water in this solution. Remember, water is a solvent, and solvent makes up the majority of your solution. And water has lone pair electrons on the oxygen. Those lone pair electrons can make a bond with the H plus to form these new species called H3O plus. The reason it's H3O is because there's an additional H to the water, and then the reason there's a plus is because that H that's added has a plus charge on it. This species H3O plus is called a hydronium ion, but in terms of the chemical behavior of the hydronium and the proton, they're basically the same. So you'll see a lot of times that we would write this equation even though H plus doesn't really exist, but what exists is H3O plus. Now, the Arrhenius base is something that contains hydroxide, so sodium hydroxide in the aqueous form will be an example of this. The Na plus and the OH minus ions, they're separated in water. Now, it turns out that the definition that Arrhenius gives is not really covering all the different acids and bases that people know of. So as a result, a second more general definition was introduced by Bronsted and Lowry. So in this case, an acid is something that can give away its proton, and a base is something that can attract the proton from the acid. Let me use the example of HCl again, which is something that we saw earlier was defined as an acid by Arrhenius. If I take HCl and put it in water, how can I show that HCl is a proton donor? Well, the way I can show that is by writing HCl and then explicitly including water here as the proton acceptor. So HCl is going to give away its H plus to water. Now when HCl gives away its H plus, what's left is Cl, but then of course the plus is also taken away, so then what's left is Cl minus. The water accepts that H plus, so one more H makes it H3O, and then because there's a plus there, it becomes H3O plus. So this would be the way you would write the reaction of HCl as an acid. HCl lost its H plus, so that tells you that this is the donor, so that's the acid. The base is a proton acceptor, so water is the one taking away that proton. The water plays the role of the base in this reaction. This is just a Lewis structure that shows a little bit more clearly how that proton transfer reaction occurs from HCl to water, okay, forming the Cl minus and the H3O plus ions. Now here's where Bronsted-Lowry really becomes useful, is showing that a lot of bases don't need to have hydroxide for them to serve the role of bases. So here's an example. NH3 being placed in water has characteristics of a base. In other words, it can neutralize acids and other things that we observe with bases in general. But using the Arrhenius definition, there's no OH in this formula, so it's really hard for us to explain why that would act as a base. But if you use the Bronsted-Lowry definition, you can see that if you put NH3 in water, water now can donate a proton to NH3, forming the species NH4 plus, because it's getting an H, so it becomes NH4 and gets a plus as well. The water loses that H plus, so what's left is just the O and the one H, and then because the plus is also taken out, what's left is the minus. Okay, so it's OH minus as a result. So in this role, you can see that NH3 accepts or takes away proton from water. So water is a proton donor or an acid, and NH3 is a proton acceptor or a base. So this is a Lewis structure drawing that shows you exactly how that process occurs. Keep in mind that your Bronsted-Lowry base would always have at least one lone pair of electrons because it needs that in order for it to attract the H plus from the acid. Okay, let's see if we can apply that Bronsted-Lowry definition to recognizing what's an acid and what's a base in a given reaction. So the question here says to identify the Bronsted-Lowry acid and base in each of these reactions. Now again, the way you identify them is to remember that an acid has to donate a proton and a base has to accept a proton. So if we look at the reaction from left to right, so we're trying to look for a change in one H plus. So we notice that there is a change from H2SO4 to HSO4, and that's a loss of one proton. And vice versa, if you look at the H2O versus H3O plus, you notice that that's a gain of a proton. Okay, so then if you're donating protons, so this has got to be an acid, and then H2O, which gains a proton, that means it's accepting a proton, so then H2O is the base in this case. Okay, so similarly, let's take a look at the next problem. We have HCO3 minus with H2O to form H2CO3 and OH minus. And again, looking at the change of one proton, we see that HCO3 has gained one proton to make it into H2CO3. And the way I know that is because, here I only have HCl CO3, and here I have H2, so that tells me that there's one additional H. And then the minus becomes neutral on the right side. That means that the minus has been neutralized with a plus, so that's why it gains one H plus. The H2O, on the other hand, becomes OH minus, and the only way it could do that is if it loses an H as well as a plus. So that one is loss H plus. And so going back to our idea, if you gain H plus, that means you're accepting a proton. So this is a base or bicarbonate ion, and then H2O in this case has lost a proton, so it's giving away a proton, so that's an acid. Okay, let's talk a little bit about the strength of acids and bases. That's really what causes them to react, and the reaction has a different end results depending on the strength of each of these components. The way we measure acid strength is we're trying to figure out how much H plus does the acid produce. Really strong acids produce a lot of H plus. It will react with a lot of things. So weak acid produces H plus, but not a whole lot, so there's not going to be as severe a reaction. So really in this case, what you need to do is memorize the strong acids, and then anything that's not part of this list is going to be considered a weak acid. So the strong acids, there's 6 of them that you need to know. Nitric acid, perchloric acid, a hydrobromic, hydroiodic, hydrochloric, and sulfuric acids. Okay, and then everything else, if you're given anything that's an acid that has an H at the beginning and ends with AQ and it's not one of those 6, then it must be a weak acid. Bases, we're measuring the hydroxide ion concentration because that's what a base produces. Strong bases as hydroxide salts that can produce a lot of hydroxides, so that means they have to dissociate completely. We're talking about soluble hydroxide salt, the group 1 and some of the group 2, which are listed right here. And then the weak bases are everything that's not one of those guys. And I asked you to remember ammonia. So ammonia is unique because it's a weak base but doesn't have any OH in them. If we have a strong acid, what we mean is that when we take that acid and we put it in water, in the solution, what we will see is H plus and Cl minus. We wouldn't see any HCl aqueous present. So in other words, the molecular form doesn't exist anymore, only the ionic form exists. So this is what we call 100% dissociation. Weak acids, on the other hand, if we write HF goes to H plus and F minus, in solution, what we actually would see are the molecular form, but dissolved in water. Only a few of the ions would be present, maybe 10% dissociation or 5% dissociation, so a smaller percentage of dissociation compared to a strong acid. With strong base, sort of the same idea, Na plus and OH minus would be observed. If we put this in water, we wouldn't see the NaOH at all, whereas with weak bases, we can write this reaction and we notice that it forms these ions here, NH4 plus and OH minus, but what we will see in solution is mostly the NH3 species. We wouldn't see much of the NH4 plus and the OH minus. So the idea being that with strong acids, we would see mostly the products. With weak acids or weak bases, we would see mostly the reactants.